Welcome to The Code. Construction, design and engineering. This is India's #1 construction podcast.
Hi and welcome to The Code. This is India's #1 construction podcast. कंस्ट्रक्शन, डिज़ाइन और इंजीनियरिंग के इस सफ़र में आज मेरे साथी हैं रमनजीत सिंह वालिया साहब और एक स्पेशल गेस्ट हैं हमारे साथ. ही इज़ अ बिग नेम. एवरीबडी इन द सिविल इंजीनियरिंग वर्ल्ड, इन द कंस्ट्रक्शन वर्ल्ड नोज हिम. P Rajamane साहब, and he is here today with us. और रमन सर उनका इंट्रोडक्शन आप सबको देंगे.
So today we have Dr. P Rajamane sir with us, and he is a renowned scientist in the country and across the globe also. He has done extensive work in geopolymer concrete. He was a founder of Advanced Material Testing Laboratory in SERC Madras, and today we have him with us. He will talk about geopolymer concrete and other topics also. So please sir, over to you.
Good morning sir, how are you?
Fine.
I first of all want to thank you at the very beginning of our conversation because we understand how valuable your time is. Especially आपने पूरा अपना important समय निकाल कर आप हमारे पास आए. We've been speaking about a lot of things before we started recording and it is a pleasure and a privilege sir. मैं शुरुआत में ये बात बोल देता हूँ. Please, would you like to add something to your introduction? Would you like to tell us a little bit about yourself, please?
Actually, you put the topic as a geopolymer.
Yeah.
Geopolymer is a binder.
Yeah.
And binder is the most important thing in the construction world. So binders can be organic or inorganic.
Okay.
And construction world has been very fortunate because we had Portland cement as a binder available since 1824, where Joseph Aspidin patented it in UK.
Yes.
But it became very successful only after 1910 or so, because original Portland cement was basically it was with water it will set and get very high strength compared to the lime. So it became successful. But at the same time it was not very workable. There were some technical points were there which were cleared off later on. So Portland cement became workable cement so that it will have sufficient time for workability.
Yeah.
Then later on they started producing the plant, cement plant with perfect quality control, everything. Then how to use it in the buildings. And buildings were earlier only with walls. There were no actually beams and column concept at all.
Okay.
Then 1910s in New York, one building was built with only beam and column. At that time this cement was used because cement had very high strength compared to lime. And tension can be taken by steel was known. So knowledge about mechanics is well known even earlier to that, more than 200 years back.
Yes.
Now this mechanical engineering thinking, mechanics thinking, strength and stress thinking, all were understood and studied and applied for making a RCC. So let us, a structure will have a tension and compression naturally.
Yes.
So let us give the tension to the steel and let that compression be taken by concrete. And this building came up, everybody shocked. There is no wall at all.
Wow.
Then slowly it became, initially they were not accepting it. Slowly it became acceptable and now we can see nobody can build without RCC beam and column.
This was a high-rise building you're talking about in New York?
Doesn't matter. It is high rise or low rise, doesn't matter at all.
It was a reinforced.
Even one floor, one story building now beam and column, 2-story building, beam, even though up to 5-story beam and column concept is not required. Actually masonry is better for so many other reasons.
Yeah.
So that's how it started, and later on Portland cement was developed a maximum to the extent of chemistry so much. But it took another level because they started making how to make the cement to work for more time.
Okay.
Then they found the admixture for that. So it became a new concrete now, where you can make the concrete to work for more time.
Yeah.
But no, another research came out they found out in 1948, so there are papers by Powers and Brownard, 9 papers in American Concrete Journal. Wonderful work by Powers and Brownard. And T.C. Powers has written many other books also. In that publication, it came out clearly that lower the water content, higher is the strength.
Okay.
By real microstructure experiments, which was already done in 1910, 20 or 19 some other period. We'll put that Adams Smith. Actually, he has proved that lower the water cement strength is high, and he found out that actually we don't require aggregate and other things for importance. Their contribution to the strength is not on so much high side as towards the cement and the water content. And he developed an equation for that. It shows that lower the water content, higher the strength. He proved by experiments.
Right.
And that was done at microstructure in this paper, these 9 papers. And it proved how much water is going into the chemical reaction.
Okay.
And that became only 0.23. And by that time, Portland cement was standardized in the chemical composition. By that time. So cement is made out of 4 compounds. Everybody knows Bose compound.
Yes.
And Bose compound, they found out that it explains the cement behavior properly. And Bose compound can be made separately also. And they synthesize separately studied their properties. And when the cement plant is making the cement, they found out these 4 compounds, how much they are there, because they are all mineralogy. And they are using this combination of this Bose compound, they could actually predict what is the behavior of the Portland cement. Then the cement production went to another level. How do you control this Bose compounds, proportions? And there is a limit for that, because we have to use basically limestone and clay and everything for making. There is a limit for that. So, but they could find out. So again, cement strength goes on increasing now.
Yeah.
Because of this knowledge. And they also found out what is the basis of the fineness of the cement. And Adam Neville, Adam Neville, he is the best book on the earth, and anybody is working on concrete. I am making this statement everywhere, and this even now it is valid. Anybody is working on concrete, either designer or analyzer or scrutiny or anybody, he touches and thinks about concrete or looks at concrete, he must read this book.
Wow.
If he understands or not, no problem. Let him not understand, but at least let him read once.
Yes.
Adam Neville. A.M. Neville, and he has written Properties of Concrete.
Yes, sir.
Another book is Concrete Technology.
Concrete technology.
So this book explains everything on so wonderfully from his heart. He is not worried about the science and technology so much. Okay. He says whether it is right or wrong, he will write, otherwise he will not write.
Yeah.
He will criticize it. For example, he criticized the fly ash concrete being taken as the wrong cement. That is Portland pozzolana cement. People found that adding fly ash increases the carbonation. Test results are shown, so many. It was a valid result. But he found out that it was not correct.
Okay.
Because basically fly ash changes the microstructure of the concrete. And the microstructure changing means, pores are reduced. Permeability is reduced. Permeability is reduced means everything should become all right.
Yes.
Now why these wrong results are coming? And he clearly showed that it was because of the test conditions it was showing. Fly ash reaction is slower, and you remove the Portland cement and put fly ash in that portion. There is less cement in that Portland cement. That is a fly ash reaction, it takes more time.
Yes.
To come to the level of the microstructure of the original Portland cement.
Strength, yes.
So in 28 days, if you do it for 90 days, you may get the better results.
Yeah.
Nobody bothered about looking at that in the initial days.
Okay.
So they were testing at 7 days, 28 days, they are comparing. Because scientists are starting only thinking of comparison. That's why they got wrong results.
Yeah.
At 28 days, naturally porosity of the Portland cement, pozzolana Portland cement is slightly more than that of the Portland cement alone. Later on, when the reaction is increased, then the microstructure becomes stronger and stronger, and not stronger, more dense.
Yes.
Means lower size pores are increased.
Yeah.
Then higher size pores are reduced. By that permeability decreased. And by that time, water entry is slower, carbon dioxide entry is slower, naturally it should be more carbon resistance.
Yes.
Okay. This type of introduction he gives always in his talks when he talks about it. And I think, I don't know whether we can say, or still we can say, he says high performance concrete word itself is a marketing strategy.
Okay.
Concrete has to work. Every question of performance, high and low. Concrete also, he says that. But anyhow, from marketing side, from technology side, from practical side, let us keep that discussion separately. High performance concrete, he goes to that level.
Yeah.
Okay. Coming back to that, Portland cement becoming, very successful, and strength increased from M15 or M20 to M200, M350.
Yes.
M350. But still Indian constructions up to 1980s are talking about M20, M25 only.
Yeah.
M15, M20, 25. There's no problem about that. But later on we started working on this, what is the meaning of the strength of the concrete. Then we understood what is the actually role of this aggregate.
Yeah.
What is the role of workability, what is the role of compaction, all things we started understanding. At that point in time, we came to know that aggregate shape and size are important. And we collected the proper shape and manually. I'm talking about 1980s,
Yes.
early 80s.
Yes.
And supervisors were made available, superplasticizers are made available in India of the authentic nature, which was not there earlier. I think I must tell marketing name or not, but still I will tell you that Fosrock were the first company who brought out real supervisor to India. Before that, there were powdery based supervisor available, but they are not developed to that level. And that was used, we have studied that also, and we studied supervisor in the 1970s, early 70s by buying them from Germany and Japan in ACRC in Chennai, because we were working on fiber reinforced concrete.
Right.
In fiber reinforced concrete, workability is reduced. How to improve workability?
Yes.
At that time itself, we were aware that the supervisors will do the work. And already Japanese have worked on that, Germany. We imported and used and found that it is working well.
Yeah.
Okay.
That is the beginning of thinking is like that, always think in the future. Then Indian supervisors were available in the powder form. We tried that. Somehow consistency was not coming. Though it is okay, but it was not consistent. So we felt, okay. Then later on when Fosrock people came, it was very good. Then we started working in the highest strength concrete. Because supervisors, if you put more than the required dosage, it will reduce the hydration. It will affect the hydration. It should not affect hydration too much.
Okay.
So these Fosrock people were able to formulate in such a way that it doesn't affect.
Yeah.
Right.
Because earlier they were mostly lignosulfonate based. Later on, as the Japanese and German did, they went for this sulfonated melamine formaldehyde and sulfonated naphthalene formaldehyde. Those kind of things came, and they were better than lignosulfonate because lignosulfonate was the sugar based. So this worked better, and we worked on that, and we made, and also supervisor became. Then mixing also, we mixed properly with correct amount of supervisor. We should produce 129 MPa in 1980.
Oh.
129 MPa. I showed it to our director.
Yes.
And director said, what is so, you are a concrete technology, you should produce it. Sir, I am happy that it is not reported anywhere in Indian paper, anywhere in the world. So I am saying you, anyhow, it doesn't matter. So we understood the importance of the strength about the particle packing.
Yeah.
So we saw that not only cement, not in the supervisor, we should look at the particle packing approach. That means in a concrete, we take one volume, there is aggregate, aggregate means which doesn't react, and there is a binder, which is a cement, but there is the powder initially. Then water will react, and water will go away and it will produce pores.
Yes.
That means there is a porosity. So if you take the aggregate and cement alone, you mix them, you should make a mix such a way that pores are released.
Yeah.
Yes.
And that is learned by particle packing theory.
Great.
And we were happy to read about that in the one book by actually Larard, F.D. Larard, Concrete Mixture Proportioning, a Scientific Approach book, fully on the particle packing.
Wow.
He doesn't talk about two particles coming together. A lot of theories are available in physics. How the two particle sizes, let us say 1 mm, some particular cylinder, a sphere, and their smaller cylinder, when they come together, how they match, when they mix together, we can theoretically calculate how much is the porosity. Dependent how that. So this is the theoretical available for this. But what about our concrete? And when the particles are in concrete, we are not using one size. We want to increase the packing. So bigger aggregate is a coarse aggregate, then smaller aggregate, fine aggregate, like that we have to. And how to consider this? And this was all studied well by this person. And before that, there is one paper called Dever. DEWAR, Dever. I will tell that is concrete. That book is computer modeling of concrete mixtures or something like that. Is a UK RMC man.
Okay.
He has written the book on the particle packing, but his theory is only two particles together.
Okay.
He will take this particle this size, this particle this size. When they come together, what is the effect? He has developed an equation based on the studies on the aggregates and this thing. And we took that study because every time two particles together. It was simpler.
Yes, sir.
Equations are given, we went. So for concrete, we applied like this. You take cement and fly ash or cement and silica fume, make one mix. And you will find out there are only two things is required. One is the particle size. Okay, what is the bulk density? Only these two are required.
Yes.
So find out from that and find out what is the mix properly. Then that is the powder portion. Come mix with the sand now. And sand property we know basic. Then mix them and find out by theory how much is the mixing we should do.
Yes.
And that you proved by the experiment also. Then the theory also by again you take aggregate and sand and this powder portion becomes mortar powder. Take this and put to the aggregate. This is one average size you can find out. That average size you mix them and you will find out another make packing. So you can slowly build the packing.
Yes.
Yeah.
And when the packing is done, then there is a pores because of that. And the pores we can put, let us say, put a little water in that. And we know least water is always good for the concrete.
Yes.
Yeah.
Yes.
So find out what is the least water. But least water may not be working there.
Yes.
Then we will add supervisor.
Yes.
Then again these are like this we can do experiment. So experiments are possible after making at least the initial thinking on the topic properly.
We have to adopt right approach.
Right approach.
Yeah.
And whatever Lara did was, a brilliant man, he took all the particles together.
Yeah. Okay.
All the particles together and he produced an equation. And unfortunately that book, I asked many people to tell me how that formula has developed. And there is a compaction factor is there on CIF. Nobody explained me how to calculate that value.
Okay.
Including the person whose paper has been referred by him in his book.
Oh.
He is in Delhi.
Oh.
But he was working on polymer concretes. He has made packing and he has used that packing application. Experiment. He has used that data from the literature, from the published literature, and wrote in his book. Okay. So he has to find out his theory applicable to the already available matter. Now he did that Larard.
Yes, sir.
So theoretical, very fine book, very great book. Using the particle packing, he could even tell in that book what is the segregation possibility.
Okay.
What is the segregation we can calculate? What is the air entrance we can calculate? Let alone the strength also.
Yeah.
So that book is fantastic. Now, so packing theory, we understood what is the importance of packing to get the strength.
Yes.
It is not the binder alone. Packing also gives the support. And one important is water is available here for the chemical reaction. So least water is required for the chemical reaction. But unfortunately, the water requirement for the chemical is only 0.23.
Yes.
But 0.23 we cannot apply it to for working ability.
Yes.
So we'll add more. But very important, 0.23 goes into chemical reaction. But after reaction, there is a volume production. That volume goes nearly up to 0.36 or 0.38. Okay. That means we must have created the volume inside. That means 0.38 minus 0.23. You can say 0.15 extra we must add. So that 0.23 is reactable.
Okay.
Available. So minimum is 0.38 water cement ratio will produce what is called zero porosity, capillary porosity concrete.
Okay.
But again, porosity, zero capillary porosity we are talking. If the water is less than that, capillary porosity will become zero definitely.
Okay.
But cement may not hydrate fully.
Okay.
Doesn't matter.
Yes.
Pores are less. Because there is another called gel pores.
Yes.
Gel pores are reduced. No problem. The strength will come.
Strength will come.
So this is how we understood the meaning of this concrete as a volume.
Okay.
Then we wanted to make it, more workable and things like that. Then we started making actually the self-compacting concrete.
Yeah.
Self-compacting concrete. Admixtures are available. So that this thing is removed.
Yes.
Vibration is removed, so that compaction is by automatic.
Yeah.
Yes, sir.
Then the next question, we worked on the first time in the country.
Yes.
Self-compacting concrete.
Okay.
Then again there is a question of use of more fly ash.
Yes.
We found fly ash is a must for concrete. Fly ash meaning is pozzolana material is a must for Portland cement concrete to improve its durability and the strength also.
Yes.
Strength I am talking about the final strength,
Yes.
not 28 days
Yes.
strength.
Yes.
So definitely we have to add a fly ash, or we can say pozzolana material,
Yes.
or we can say a finer material, so that it even we can say compacts. There is a binder. There is a more compact binder system apart from the Portland cement, and this powder together will become more compact.
Okay.
Yeah.
So that then it becomes silica fume available.
Yes, sir.
So worked on the silica fume. It also worked very well.
Yes.
So we understood that, and we were making that. Then how much we can, because we are understanding what is the meaning of porosity and packing theory. We went, and also reaction system we understood. We went towards the adding more and more fly ash.
Right.
And our grade requirement, concrete requirement went from, we can require concrete or Portland cement matrix from 10 MPa to even 100 MPa, 200 MPa.
Yes.
So when such a great requirement is there, so let us see how can we get it. So our idea was to use more fly ash. One is towards the microstructural improvement, that is one side, and the how to use more fly ash. Fly ash is the waste material requiring a proper disposal.
Yes. Yes.
So we went up to 80% to 70% fly ash content in cement concrete.
Okay.
Okay.
Don't worry about theory. I mean, don't worry about IS codes.
IS codes. Yeah.
We are looking at the structure.
Structure. Yes.
And this properties.
Yes.
And we found that a 70% replacement, we can go up to M40, M50, M80 easily.
Okay.
Right.
But there are other sides. Let us look into whether should you go for that Portland cement in actual, because more important civil engineering long-term properties.
Yes.
Yes, sir.
So unless a long-term properties and also statistical nature of the property we are getting, unless we are sure about it, we should not immediately by getting some values at one or two experiment, we should not jump into conclusion and recommend it. That is not the proper idea.
Yes.
So we worked on then we restricted up to 50% fly ash and worked a lot on that.
Yes.
It was sufficiently okay, and we did also prove that using more fly ash produces the lower alkalinity.
Okay.
And lower alkalinity of the cement concrete means lower electrical resistance.
Okay.
And lower electrical resistance means higher corrosion resistance.
Okay.
Because corrosion is nothing but electrochemical current flowing for anodic cathode.
Yes.
And anodic cathode, if the resistance root is very high, naturally our corrosion is less. And this is the basics of the fly ash concrete,
Right.
or pozzolanic concrete, or PPC.
Okay.
And these people were not earlier thinking about this, and they were thinking that if we add fly ash, it will produce carbonation. We wanted to look at that point also, and luckily, fortunately, the CPWD came to us, and they were interested in pushing fly ash more into the concrete. They gave us a big research project on fly ash concrete.
Yes.
And we made actually a prototype beam and column, and converted a room into a carbonation chamber, and we put these beams and columns with reinforcement with cracks. We created the cracks also. What is the behavior of the cracked specimen? As per the code, we are allowing cracks in RCC.
Yes.
That they were put, and we proved that fly ash concrete always gives a far better durability than Portland cement alone. Experiments were done, so fly ash became a very our choice material for many purposes. Then we went into this use of more fly ash up to 70%. As I told you, we can make plain cement concrete, no problem. Up to 70% we can use, no problem. Because we are not worried about strength. We want small strength, we can go up to 70%. But when you put RCC, we are worried about some alkalinity also. Too much alkalinity, less also is not good in the sense. Then so we proved that 50% okay. Then code took it and put it to 35%. No problem.
Yes.
You can theoretically calculate also how much. After all, pozzolanic reaction is nothing but lime is coming out of Portland cement hydration. For that lime, how much of SiOT is required, you can calculate. We can find out how much of SiOT is available in fly ash. We can do theoretical, can put it. So there is no problem. So we proved that, and we went into this high volume fly ash concrete, and also fly ash concrete as a better material, and more fly ash we wanted to use. Then at that time we made the fly ash itself as aggregate.
Yes.
That means two ways. One, you put extra fly ash. Initially it is not acting like a binder as a reaction is slow.
Yes,
it is a binder, it is a filler.
Filler.
So we can call it as a filler and calculate our packing theory. We did that work.
Okay.
So fly ash as a sand replacement material, we wrote a paper.
Oh.
And that paper we developed the equation also for that based on our work. Then it was well received in the whole world. It was developed, it was put in Cement and Concrete, it's a composite journal, and it came out all right. Now we have made aggregate also in the laboratory using fly ash. They were lightwood aggregate but without burning. Because lightac was a very common aggregate in UK where they were doing sintering.
Yeah.
Okay.
To convert that fly ash into nodules.
Yes.
So it was very successful. And so many, because their lightweight aggregate is very much required there in those countries because of the requirement of the high insulation property of the concrete in those cold countries.
Yes, sir. Yes.
And also they use it for bridges and building, no problem. Lightweight aggregate concrete was very successful there.
Okay.
Now our idea was not lightweight aggregate, our idea was use more fly ash.
Yes.
So we converted that fly ash into aggregate in SCRC, only room temperature curing. Sorry, not room temperature, not sintering. So we could go for the cold bonding, you can say, they call. We can use only a proper amount of cement and lime and produce the nodules. And the nodules are sufficient to produce up to M40, M50 grade concrete.
Great.
We worked on that. So we were so much interested in fly ash. One day we thought, why not we use the fly ash itself as a vendor in one sense, because we have gone up to 70%, 80%. But for that, now we are not knowing what is the route. Then we found David Oates has worked on this aluminosilicate system in France, and B.V. Rangan has worked in Australia.
Okay.
And he has used only fly ash for making the binder.
Okay.
But his route was making it reaction. What he did was he didn't use fly ash, cement. He didn't use Portland cement with fly ash. The route was not actually the original one. Yes. That is original for the PPC concrete. But now he used directly fly ash.
Yes,
then he had to go to the geopolymer route. And geopolymer route was given by David Oates.
Okay.
What is geopolymer route? You take one alumina source, you take one silica source, bring them together, add some alkaline situation there. You create alkaline situation. So alkaline situation is created by either sodium hydroxide solution or by sodium silicate solution or combination of that. Now this system is having high alkalinity, and because of this alumina and silica will come into the solution because of alkalinity, and there is interaction between them, and we get a sodium aluminosilicate system.
Okay.
Cut.
So
कुछ आवाज आ रही है
कौन सी इसी की सर ने जो भी कहा है उसको एक सम अप
And now I think here it was coming. Some automatic video was on.
Yes.
Okay.
No, it doesn't matter.
Okay.
Start करें sir.
It's not so disturbing, no? No, it's okay. Now shall I continue?
So, till now what he has covered वो थोड़ा सा एक वो
आप कर लो
हाँ. So
1 minute. I will now I will make the starting of geopolymer, and then we can. So geopolymer was like this aluminosilicate system.
Yeah.
It was alumina silica source we are taking. We are making them to come together, and they will make a molecule. But what happens? Alumina and silica is polymer silica will form. There is no doubt. Polymer silica is a well-known factor. Now polymer silica is having silicon-silicon bonding.
Okay.
But silicon will not react bond with silicon directly. It will bond through only oxygen.
Okay.
That is whereas carbon is not like that.
Okay.
Carbon will bond to another carbon directly.
Okay.
Here it cannot bond. There is a rule for that. Okay. Now this in this polymeric silica, if you remove one silica, put alumina in that place, it becomes aluminosilicate.
Okay.
Now what happens? This aluminosilicate, aluminum is 3 valency. Silicon is 4 valency. You are removing silicon, you are putting alumina. There is 1 valency left. For that you have to put the sodium.
Okay.
Sodium is 1 valency. So sodium plus aluminum 4. Silicon is this thing. Then it becomes neutral. All molecules have to be neutral electrically. So it has become a neutral molecule. This is sodium aluminosilicate. Now question is, instead of sodium you can put potassium also. It is also single.
Yes.
So that group is there now. So those group periodic table, that group, all the elements can be put, including KCm and things like that. Anyhow, so this either sodium or potassium, but sodium is more easily available, so we work with more sodium hydroxide because sodium is from the seawater. Now this is the sodium aluminate silicate system. It's a basic.
Okay.
And this, because aluminum silica is available on fly ash, we took it and started working on that.
Yes.
Now, so this is a sodium aluminosilicate because we are having a polymeric silica already known about it. We are removing aluminum and silica and putting aluminum in that. We get a binder. Now this becomes a binder. Okay. Polymeric silica is different.
Okay.
It becomes coating and other things. But now we are wanting a Portland cement type of binding system. So this work was done by David Oates.
Okay.
But for that he used pyramid structures. Okay. Pyramid proved that the sodium aluminosilicate system is made there.
Okay.
And that is a binder. Okay. That is not actual artificial, that is not actual natural stone, it is artificial stone. Okay. And he got those minerals from that Egyptian area.
Okay.
And he created the reaction in his factory and produced the stone.
Wow.
And the stone is called geopolymer. For first time he patented the word geopolymer.
Oh.
And the patent word is geopolymer, that is sodium aluminate silicate. Instead of sodium it can be even potassium also. And for that he didn't use fly ash at the time, he used metakaolin also. Okay. Later on. Metakaolin is a clay particle. And it is also in the sodium and I told silica and alumina. Later on he started working on pure geopolymer system, because when you take original mineral, it is a mixture of so many things, minerals. Yeah. And he did it from that pyramid area and he proved it. Then he started working more on this metakaolin based on nothing. He worked a lot on that. And his idea was not to produce concrete at all. Okay. His idea was to produce a fire resistant material. Okay. For the use in European tunnels and things like that. Okay. Because pure geopolymer is completely fire resistant.
Wow.
Where a Portland cement binder is not high temperature, it is maximum up to 200 to 300. Later on it loses strength very much and 500 seconds is gone. Okay. Whereas you take the stone, if you put into fire, nothing will happen to that stone. That is geopolymer.
Okay.
So that's what he did.
Okay.
And now, but his idea is different. Now we are engineers entering into that. Yes. We are not talking about the stone strength. We are requiring about our requirement. That's what was done by B. Rangan. He used the fly ash and we took that. So I am close friend of B. Rangan. I talked to him many times, and we took that fly ash. But the fly ash we didn't want to use the temperature curing. Okay. Because the fly ash reaction, as we know, is slow reaction.
Okay.
So it cannot reaction generation at room temperature with alkaline systems. Okay. It is slow. That's what we use in ordinary concrete also. We don't fly ash in cement concrete. Actually, a lime reaction is alkaline lime is a pozzolana. It is a high alkaline system that silica from the fly ash reacts and we produce the CSH gel. Okay. That is called CSH gel.
Okay.
That is the binder. Yes, here this is not CSH gel. The same, but here we are using not only silica, we are using alumina of the fly ash also. Yes. So it is a better utilization here. Okay. Both are removed and we are creating the combination of them, we get a molecule.
Yes.
And that molecule is called sodium aluminosilicate, that is the binder.
Okay.
And because this is inorganic, this is inorganic, it's definitely different from the organic chemicals.
Yes. Okay.
So this is also polymer, but that is the organic polymer different from inorganic polymer. So this inorganic polymer, we can expect it to be quite different. That's why whatever we read on the organic polymers, plastics, because general word is plastics. Those knowledge cannot be applied directly to this. Okay. So keep these two things separately. Okay. Yeah. That is the problem we are facing. Okay. I mean, when we are discussing with the people. Polymer, when you say geopolymer, they always keep polymer word in the mind and try to connect it to the plastic organic chemical. Okay. We avoided that because we are, unfortunately I was having chance to work with chemistry people in my earlier career when I was working on polymer concretes. At that time, our Professor J.S. Ramaswamy created a UNDP program, United Nations Development Program.
Yes.
At that program, we were sent abroad to study on the polymer concretes. And polymer concretes means anything on the polymer, and it was organic polymer. Okay. That thing, but this monomer becoming polymer. So liquid is taken and it is converted into polymer, that becomes solid particle for us for the reaction, for our binding, and we did lot of work on that. So one is the methyl methacrylate monomer, and there is a styrene monomer, and there is epoxy and polyester. All these things we were working. At that time we had interaction with chemistry people coming from the abroad. As UN experts, chemistry, chemical. So we had an introduction into the chemistry and chemical engineering as a basic requirement of material science for in our mind in SARC. So I was keeping that in the background. So I was trying to look at this from that background also. And in SARC we didn't have so much of chemistry people in our laboratory. We didn't have, but I was fortunate that in our campus, in CSR campus in Chennai, we had other laboratories like SACRI, Central Chemical Research Institute, and there is a NERI, National Environmental Engineering Research Institute, there is NML, National Metallurgical Laboratory. All these laboratories had their own chemistry lab also. Because it's natural for them. So I used to interact with them from my side. So they helped me a lot to understand all these points.
So when it comes to geopolymers, especially in construction, what kind of an impact can be expected and the applications of a proper use in a modern day society?
Now, anything geopolymer, when you say geopolymer concrete, now I just now mentioned that it is a binder now. It is a sodium aluminosilicate binder. Now, whether this binder is having a similar strength property with respect to concrete, we should know. So that kind of studies we made. So now in our case, we didn't use initially, we used fly ash, plus we wanted the reaction to happen at the room temperature. Because our concrete work, site work, everywhere it is, mostly we are looking at the room temperature setting only. So at that time we found that GGBS will help. Ground granulated blast furnace slag will help. Because it helps in two ways. One is, it is itself reacting with water and produce its own binding system first. In that binding system there is a calcium also there, and that calcium will help this more reaction here in our fly ash. Because I told about sodium. Sodium is one valency extra it is giving, but calcium can give two. So we added GGBS to get the room temperature. We were successful. Before that, I took 2 years to get this room temperature curing of the fly ash myself. 2 years. When I, before understanding GGBS, I was trying so many ways. Then once, but unfortunately there is no chemistry in our lab, but somehow one geology person worked as a project assistant for me. I asked him, why don't you do some chemistry work? He did. And we got first time that I put fly ash in a test tube. I did something. It got hardened. Some water added, something added, it got hardened. I took the strength, I got only 0.5 MPa. 0.5 MPa, nothing. It is, but I was happy. It was 0 to 0.5. What is the change? 0.5 by 0. I was happy. Then we worked.
Progress.
That means fly ash can become itself at room temperature. At high temperature. Then we started working, and then we came to this GGBS. It worked, and so GGBS fly ash combination we worked. But we found that GGBS is giving high strength. So I went from this angle. I was not so geopolymer man in the beginning. I am a Portland cement man. Then I started thinking about the GGBS. So I took 100% GGBS. It gave high strength. 100% GGBS over this thing, it gave high strength. High strength. Now I added fly ash. Strength is slightly reduced, but strength is good. So I went on adding fly ash and getting the room temperature curing, and strength I studied. And this, how these chemicals have to be added. I told sodium silicate solution is generic. Why I said generic is sodium silicate solution is SiO2, Na2O, H2O. These three become sodium silicate. But Na2O, SiO2 is not one molecule. NOD is one molecule, SiO2 is not one, it can be any number of molecules. It can be 1 up to 10, it can become go. It can 4, 5, 10. People are not looking into this aspect. But civil engineers, but it is already looked into this aspect by geolite people, geolites. Geolites already worked on the sodium aluminate system. They are quite aware of that. They create the reaction. But for them, what is the reaction? They take alumina and silica and they will produce the sodium silicate solution systems, and they get the reaction and produce a molecule which is a not binder, it is a molecule.
Yeah.
And they take out, that is called zeolite, and zeolite powder. It has got its own property. They study the molecular level, what is the porosity of the molecule and what is the binding property for some other chemicals and hazardous ions and things like that. They go in that direction.
Yes.
Chemical reaction system is different.
Yes.
Our system is, we are having very less amount of liquid. Their system is lot of liquids. They want to create only the solids only. So the zeolite systems, they work, but the final product is same. Sodium aluminosilicate molecule, polymeric molecule.
Right.
Only thing is, this is crystalline. Zeolites are crystalline nature. So they are not binder for us.
Okay.
Our geopolymer has to be, our aluminosilicate polymer has to be amorphous. And the way we create a reaction system, sodium aluminosilicate system production system is, generally it only becomes amorphous reaction is generated. Because we don't give so much of environment to convert it into crystalline nature. Zeolites people also do it. Their initial thing is only amorphous only. They again work on that. Their processing starts so that amorphous is converted into crystalline. And then they are happy. I am interested in talking that side also to make this geopolymer as a replacement for epoxy and polystyrene.
Oh.
Okay.
This I started working in SRM University with help of aeronautical students, because they are also working on composite. And I tried to connect it to the mechanical department in SRM University. It was the beginning only. But at that time I should not use fly ash in GGBS. Because in aeronautical people, they use FRPs.
Yes.
Fiber reinforced plastics. So lot of fiber is present, only binder is small. Okay. And binder can be small because of the liquid binder we are putting, epoxy. Okay. And that means I should create a liquid which will go inside and start reacting to become binder.
Okay.
That means I should not start with this solid particles of this fly ash where alumina silica. No. That means I should take a proper alumina solution, proper silica solution, bring them together, and can I make it to a reaction table,
liquid geopolymer,
so that it becomes a binder in the presence of fibers.
Yes.
That's
and
a special application.
And this is not new. Yes. This has been done secretly by in America, and there is one Balaguru, one professor, a famous professor. He has worked on that in Radioactivity. He has made a paper, and that geopolymer, he has used the carbon fiber, and he applied on the RCC framework and put it to the fire, and the strength was maintained.
Right.
So because he produced pure geopolymer systems.
Right.
But that he doesn't tell us in the paper exactly how he has created the reaction.
Right.
And what are the ingredients. But we understood something, and I started, but by the time I retired from SRM, I am in the Bangalore only last 3 years. If anybody is interested only on the research side, this can be done, but chemistry, chemical engineers and material science people should join. Yes. Only civil engineers cannot do work.
Yes.
Anyhow, coming back to this sodium silicate as a material, the sodium oxide Na2O and SiO2, the ratio is a very important point. Yes. That ratio is called molar ratio.
Okay.
In chemistry.
Right.
Zeolite. And also another word is called weight ratio. If you convert, suppose you put Na2O dot 2 SiO2. That means 2 SiO2, that means SiO2 by Na2 is 2.
Right.
That is called weight ratio. If you put Na2O and SiO2 in terms of grams, it becomes weight ratio. If you put in terms of how many molecules, it becomes a molar ratio. Fortunately, in this case, for sodium case, both are almost same.
Okay.
Because sodium oxide is 62.
Right.
And silicon dioxide is 60.
Okay.
So 60 is there, but if you take the potassium oxide, it becomes different.
Okay.
Say potassium molar molecular atomic weight is different. It is 40, 39, whereas the sodium is 23. Right. So potassium oxide K2O will be, so anyhow, let us not bother too much about it, but this is very important. The ratio is very important.
Okay.
Why the ratio is important? This is highly technical. Now, fortunately, this Na2O dot I told you, MSiO2 let us call, dot H2O. When these three are together, this is solution.
Okay.
Suppose H2O is large quantity, it became a solution and it is produced.
Right.
That means when you buy from the market, I must know what is the M value in that.
You said
Okay.
that, yeah.
Okay, why should I know it? Why should I know M value? The reason is, this work has been done 1910 onwards, 1905 onwards. Sodium silicate is the most mysterious liquid in the world till now.
Oh.
Because nobody tells exactly what is the nature of the molecules and atoms and things in the solution.
Okay.
What I mean by this is, I am not a chemist, but I try to understand the side of that a little bit. For let us take sodium chloride. When we put in water, it is only sodium and chloride, nothing else.
Right.
Yeah.
There is no sodium chloride at all in the water. Let us sodium hydroxide. There is sodium and OH ions. Sodium sulfate. You take anything, most of the thing, it is only directly those molecules can be converted. That is, anion, cation can be completed.
Right.
But suppose you take hydrochloric acid,
Yeah.
H plus Cl minus, completely H plus Cl minus.
Okay.
There is no HCl at all inside. All it is called dissociation.
Disassociation.
It becomes dissociated. And these, okay, let us go little bit to chemistry. These are called strong acid. When complete dissociation, it is strong acid. Sodium hydroxide is strong acid. Because it dissociates completely. Come to hydrofluoric acid. Hydrofluoric acid will become H plus F minus, also HF inside. Wherever Portland cement is used, in all those places, geopolymer can be used. Okay. The only advantage of geopolymer concrete is we are having the lower carbon footprint compared to Portland cement. It is proven and numerically shown.
Right.
We can do any calculation at any time to show for any geopolymer concrete, lower carbon footprint is less than that of the Portland cement per cubic meter.
Yes.
Okay.
Another calculation we can do is the lower carbon footprint per MPa strength for unit strength. We can do this calculation and show it.
Okay.
And this is what we have done, shown also calculation wise.
Right.
What is carbon footprint? Carbon footprint is a combination of 2 points. One is embodied energy, another is embodied carbon dioxide emission.
Okay.
Both are related to our ecology.
Yes.
So because we don't use Portland cement, we are avoiding the 1400-degree temperature required for the Portland cement manufacturing.
Yes.
That's why its energy content is always much less, because energy content of individual particles here are available, ingredients are available in the literature. We can take directly, we need not bother about doing our experiment. We can calculate. Same thing done with geopolymer and Portland cement, we can show it in just.
Right.
And coming back to the application side, one more requirement is the durability. And strengths experiments have been done for all the durability tests of the ordinary concrete for Portland geopolymer concrete also.
Yeah.
Right.
By us, particularly by our team. Us, me means always I consider my team or our team working in different places in India.
Yeah.
Not only where I am involved or not.
Okay.
Sometimes I am involved, sometimes I am not. But data is available to prove that its corrosion resistance is as much good as Portland cement, and often it is better.
Right.
Often it is better. Corrosion resistance. Sulfate resistance is often it is better because we don't have free calcium oxide in this microstructure.
Right.
Whereas free calcium hydroxide present in Portland cement, that creates sometimes sulfate resistance issues.
Yeah.
Right.
Here we don't have. So sulfate resistance is also not a problem at all. Corrosion resistance. And the one more specially we have found is the bond is very high here.
Okay.
Bond strength of the Portland cement is less, I am not telling. But here naturally it is becoming more. From the recent studies we made at atomic level, at surface level by our PhD student in SRM University.
Okay.
By using all the modern equipment like XRD, FTIR, NMR and XPS.
Okay.
And TGA, all these modern equipments are used to find out the nature of the geopolymeric system.
Right.
I am using the word geopolymeric because I don't want to use the word geopolymer directly, because we are using Portland cement, we are using GG base also here.
Okay.
So it is geopolymeric because it is a combination of binder from these two.
Right.
So we found bond strength is very high. Portland cement concrete's bond strength with steel is one thing, good thing. It is much higher than that.
Oh.
So very important. That is so because of this strength wise, durability wise, it is either equal or better than Portland cement. That means wherever Portland cement has been used, this can be used.
Any disadvantages or any shortcomings of geopolymeric material?
Only shortcoming about the geopolymer concrete is in terms of our actual production by trained people. It is requiring trained people.
Okay.
And every ingredient, especially the liquid and the binder requirement, that is called, you can call them as geopolymeric source material, we'll call them, fly ash and GGBS.
Right.
Geopolymeric source material, GSMs.
Yeah.
Yes, sir.
Those powder materials has to be properly tested and kept the record.
Okay.
So that we get the consistent test later on.
Test.
Right.
Because these are not a factory made act.
Yeah.
Okay.
Their combination is in our hands, and GGB is available from so many sources. Flash is available from so many sources. When they join together, there may be some different properties.
Yeah.
Right.
So in every time we have to understand that and keep track of it.
Yeah.
And similarly, sodium silicate solution, I told generic name, which is a combination of a market sodium silicate solution and our own sodium hydroxide, mixing it together, we get a sodium silicate solution. People call it as a alkaline activator solution, or some people call reaction generating liquid. So many names they are called.
Yes.
But all of them are sodium silicate solution only. Only that M value, molar ratio changes.
Okay.
Generally, when you add sodium hydroxide, molar ratio comes down to from the what is available in the market.
Yes.
So it can start from point of.
Yes.
So application wise, I told you wherever it has been used, Portland cement, they can be used.
Yeah.
So in our case, we have done production of paver blocks of different nature,
Yes.
Right.
different strengths.
Right.
Okay, in actual actual paver block plants,
Yeah.
or building block making plants,
Okay.
and proved that geopolymer system can be produced there.
Right.
And we have made the road,
Right.
Yeah.
demonstration road in SRM campus, university campus,
Yeah.
and also in Chhattisgarh campus, one thermal power plant campus, without the actually use of the road engineers expertise.
Yeah.
Okay.
If road engineers expertise comes in, it will go to another level.
Yeah.
Okay.
It was a civil contractor who built it.
It will go to another level.
Yeah.
Right.
But we have proved that concrete can be made. Okay, that is one. And buildings have been also made.
Yeah.
One building is made using from the foundation to the top.
Yeah.
Right.
By that we learnt.
Okay.
And that engineer was ordinary practicing engineer using Portland cement systems for his many of the RCC constructions.
So I want to take this moment and I want to actually take an advantage of this moment with sitting with you. It's a little off topic, but there is a lot of debate, especially within the audience and within the internet, saying that fly ash has radioactive properties.
Radio.
Right. So whenever products like AAC blocks, concrete members which use a lot of fly ash are being discussed, people profess that there is a big radioactive nature with fly ash. Now when we use materials like fly ash based or Portland cement using with fly ash and concrete based on that, and now we are talking about geopolymers, they all use fly ash. Are there any long-term actual health benefits, health adversities or adversities from that radioactivity, if at all? That is a question.
Okay. Very interesting point. I looked into when I was working in Portland cement.
Yeah.
LKACERS, SEARS, there is a book, Beneficiation of Fly Ash or something. There is a UK book, long back.
Yes.
He proved that there is no underground water pollution due to the fly ash being stored for years together.
Okay.
And that was proved in Vijayawada by some other people also in their own way. In one seminar I found that Vijayawada thermal power plant has not produced any pollution to the underground water.
Okay.
Okay. Now, that L.K. Sears book, he was talking about fly ash. He found only in some places in Italy, some fly ash, because of the coal being from the earth, there is some kind of a radioactivity. But radioactivity materials are available all over the world, including in our hair. And only one place where it is, but we have to look at the radiation levels. So BIRC has come up with a radiation level.
Yeah.
How much we can measure, we can be tolerated. So any point they will measure the radioactivity. And in India, the radioactivity is much more in Rajasthan, some areas.
Okay.
They have measured it because of the local material. But still that is much less than what is accepted as a safe.
Safe now. Okay.
Even though it is more than usual, but it is much less. So now with all these points, fly ash is not at all having any radioactivity as a major problem
Health
for
hazard,
health.
yeah. It's a very big question. That's why I sort of asked you this
But
question.
what happens, scientists are so much interested in their own way, and all these radioactivities must be in the parts per billion or parts per trillion. They are never in parts per million.
Yes.
Okay.
And parts per billion and parts per trillion work can be done only by nuclear oriented people.
Yeah.
Right.
And this radioactivity is a topic of some scientists. Like I got my own colleague in NGRI, National Geographical Research Institute in Hyderabad. She was asking me, sir, we want to work on the radioactivity systems of the fly ash. Let us get some projects. She was telling me, my
Fair enough.
earlier scientist. So this is a fact. This radioactivity materials are available all over the natural earth material. Only we are talking about the content.
Yes.
Right.
That's all.
Absolutely. You wanted to do the
About the cost.
Right.
the cost of geopolymer.
We are not about our
yes, sir.
cost wise.
Let me pose that question so that we can actually cut it properly. We've spoken about the benefits, advantages, applications. What is the cost of geopolymeric concrete, and is it comparable to the traditional pozzolanic concrete that we make using cement?
The cost we are calculating per cubic meter. Actually, this is not the cost at all in the project. We should look at the project cost.
Yes.
Project cost comes out of the benefits. And the beneficiation of that, our material has to be quantified in terms of finance,
Yes.
economics. That aspect has been not done because we don't have so many site projects.
Okay.
Okay. Coming back, so what you are talking is per cubic meter only. That means ingredient cost. Even though ingredient cost is more, it may work out cheaper in some case. For example, I will tell you self-compacting concrete. Self-compacting concrete per cubic meter definitely higher than vibration concrete.
Yes.
But if in a structure, definitely cheaper because you are avoiding the vibration and you are getting a better
Flowable material.
better structure, more refined structure and more we can say quality structure.
Yeah.
So definitely its own value. So that way, self-competing concrete, even though it is costlier than vibrated concrete because we have to add some extra admixtures and we have to add actually some kind of a mix design, make a mix design such that it is different from that.
Yeah.
So per cubic meter wise, only ingredient cost may be more, but still it is better.
Yeah.
No, so now we are talking about only material cost now.
Yeah.
Ingredient cost. Again, it depends upon the sodium silicate solution we are buying and sodium hydroxide. What is the content we are buying, quantity we are buying.
Yeah.
For example, sodium hydroxide solution, it is available on 5 rupees to 20 rupees per kilo.
Okay.
Depends on how they are purchasing.
Yeah.
50 kilos are drums.
Yeah.
Yes.
Similar to sodium hydroxide, I found sodium hydroxide is generally available in the powder form. I found it is available from 30 rupees to 50 rupees.
Right.
You can see the difference. Okay.
Yeah.
Having said all these things, okay, we get what we got from the market. We try to do the calculations. We found most of the time for many grades of concrete, hardly it is about maybe 15%, 20% more.
Right.
And this more is towards the lower grade of concrete.
Yeah.
Because the difference between geopolymer and ordinary concrete is only Portland cement.
Right.
Portland cement is 7 rupees per kilo or 8 rupees per kilo.
Yeah.
And when you are paying that amount, whatever Portland cement amount we have now saved here, that amount should be available for my solution.
Yes.
So it depends upon the mix design. So that means, usually higher cement content is available for higher grade of concrete.
Yeah.
So higher grade of concrete may become more competitive here. So my initial calculations showed that if it is M40 and above, it may match, it may become low also.
Right.
Okay.
Because
M40 and above.
the admixture cost and all, it will increase in that high grade.
Considering
So,
that.
yeah.
And we are talking about cubic meter.
Yes,
But
per
if you
unit.
consider that cost of the curing and the
Yes.
environmental friendliness,
Yes,
Yeah.
yes.
which cannot be held at all.
Yes.
There is
yes,
no cost of water. There is no cost of curing.
One more thing, you are right. Curing water we have avoided.
Avoiding.
Yeah.
Yes.
And I will tell you one thing. I have calculated. I asked many construction engineers this country 1 year back. I asked them, you tell me how much of water is used for curing.
Yeah.
I want the number. Don't tell me how many days of curing. Nobody told me.
Yeah.
Okay, I did the calculation.
Yes.
Curing is what? You have to make the water present on the surface of the concrete.
Yes.
And what happens to that water? It will evaporate.
Yes.
And what is the evaporation? Evaporation depends on the temperature.
Yes.
And evaporation depends upon the radiation energy. And depends upon the vapor pressure there.
Yeah.
Okay, all this calculation I did it myself. I took this parameter and did the calculation. And what happens is you are putting the water, it will start evaporating.
Yes.
You have to keep back the water there.
Yes.
Because you have to maintain some level of water.
Yes.
And that water, so for 28 days some water is lost. How much water is lost? I did some calculation one way.
Yeah.
And I found it much more than of the mixing water.
Mixing
Yeah,
water.
of
Yes,
course.
yes.
Oh my God.
Yes.
मिक्सिंग वाटर की वॉल्यूम ही अपने आप में बहुत होती है.
Okay.
Sir, even at a ready mix concrete plant, water is involved at all times. So, even if we have average quantity of water per cubic meter is around 170, but the total water they are using is more than 300, 350 per cubic meter.
Because you are using for cleaning and
cleaning and all.
naturally. Very good. So this point, actually I want somebody to work on this aspect.
Yes.
Interesting.
Water used for actual curing,
Yes, sir.
quantification of that.
Yes, sir. Yes.
Let the number come.
Yes.
Then the number, if you no, because and this can be reduced in ordinary concrete also.
Yes. Yes.
This curing can be avoided in curing concrete. Also. I worked on that aspect.
Yes, sir.
That is called self-curing concrete.
Self-curing.
We have done work on that. I have done lot of work since 10 years, 15 years.
Great.
My point has been there only of durability aspect of the thin members. I have not yet got any time to work towards that.
Yes, sir.
But I have proved that self-curing concrete is almost same as ordinary water-cured concrete by change of only 3% at the same level.
Yes, sir.
But I will change the water cement ratio and get the same strength, no problem at all.
Yeah.
So this I have proved using particular type of self-curing chemicals available.
Yeah.
Oh, great.
I have done the experiment on that, but I am not happy yet to present it to the world because we have used 6 inches cubes
Okay.
and we used beams and columns.
Oh.
Beams and columns I am talking.
Yes.
Beams and columns for structural behavior with
Right.
self-curing, curing and no curing.
Yes.
We found it working well.
Right. Great.
Now problem is only about the, suppose can you use it in ferrocement? Can you use it in the repairing?
Yes.
So repairing, you use a plastering, very thin member. So this aspect has to be studied in more detail, which we have not done yet.
Yeah.
Then there is a missing.
We definitely need to work on that.
No, I will
sir.
tell you, RMC people,
Yes.
you work toward that and get confident that it works in this. You please add that chemical in your RMC plant. Prove, tell that our concrete doesn't require curing. Over.
Yes.
Let me do one thing. Let me do the closure, and
yes,
then
yes.
we can save it and we can close it.
Sure.
Rajamane sir, thank you so much for your time today. It is definitely an eye-opening and a very informative session that we've had with you today. I know that we have not even scratched the surface of the technical details and the chemistry of the product that we are talking about, but it gives us a fair idea. I think we will fly back here once again to do a comprehensive talk on geopolymers, applications, production and other aspects with you again. With me and Ramanjeet ji, I thank you a lot, and you have no idea how thankful we are today because you've opened up our eyes. This was Dr. P Rajamane, and if you have any questions, write to me at India's #1 Construction Podcast at gmail.com. You can follow me on Instagram at India's #1 Construction Podcast. We would love to hear your questions. We will forward your queries to sir, and sir may find some time and answer your queries as well. Signing out, Ramanjeet Singh, Walia and Rishabh Aggarwal, your buildmate friend, with Dr. P Rajamane from Bangalore. Thank you so much. This was The Code.